In this lesson, we are looking at Euler's method. I know it looks like the word Euler, but it's really the word Euler, Euler's method. Students will use Euler's method to approximate a particular solution of a first-order differential equation. So instead of actually solving a differential equation to find y equals, Euler's method works as a way to approximate what the value would be. I always think of it as kind of like a connect the dots. If I scroll back here to our slope fields from the last lesson, Euler's method would almost pick a point here, and it takes a little step based on the slope, plots another point, takes another little step based on the slope, plots a point, takes another little step based on the slope. So it won't give you the actual function, but it would give you a numeric approximation for the differential equation that you're dealing with. So Euler's method is a numerical algorithm for approximating a particular solution, y equals y of x, of a first-order differential equation, where dy dx is defined in terms of x and y. With the initial condition x equals x sub 0, then y equals y. Let's say this should have a sub 0 on it. It begins with the initial condition x sub 0, y sub 0, and then uses a small increment h in x called the step size. We've seen h before when we were talking about limits and that definition of a derivative. So h is kind of like that delta, the change. The first approximation to y equals y of x is given by y equals the original y plus delta, I say delta, but h times the function, meaning the differential equation evaluated at those first 2 points. And all following approximations are built on the previous one. So kind of like derivatives, if you need the fourth approximation, you can't get there unless you do the first 3 approximations. Each approximation follows the tangent line to the graph of the solution to the differential equation. It follows the slope field. So this is just a particular piece of that slope field, but here's my first point. Using the slope at that particular point sends me up here. And then, you just plot more points. So formula for Euler's method. This one is written a little bit differently than the one that was given to us. If I use the one up above, I could even say y sub 1 is y sub 0 plus h, also known as your delta x, and then your differential equation given at that point x, y. So these two are a little bit closer to each other. This is just the version that came with this diagram. So example 1, suppose y equals y sub x, or y of x, is the solution to the differential equation dy dx equals xy plus x squared. With the boundary condition, if x equals 1, then y equals 2. Use Euler's method to approximate y of 1.75 using h.25 as the step size. So, if I use the formula that's written in green above, y sub 1 is going to be y sub 0 plus h, and that differential equation, I could do it this way, evaluated at x sub 0, y sub 0. So, y sub 1 is going to be my initial y value, h is my step size, and now we want to evaluate that differential equation. So this is my xy plus x squared, and that's at the 1 and the 2 right now. So x equals 1, y equals 2, plus 1 squared. For these problems, you're expected to use your calculator, and that's completely fine. So when I evaluate this, I have 2.75. Just a reminder, this is a y value. This is your new y value, y1. So if we want to find y2, I go back, I use the y value from the step before, so this is 2.75. My h remains the same. We have a new x this time as well. So if my initial x was 1 and my step size was 0.25, then this is 1.25. times my y value from the step before, which is 2.75, plus my 1.25 squared. I'll use my calculator to evaluate that, and this time I get 4. The next one should be 1.5, so y3 would be 4. That h remains the same. My x value, again, we're going up by 0.25, so here's 1.5. There we go. My previous y value of 4 plus 1.5 quantity squared. When I do this iteration, so when we calculate y of sub 3, this becomes 6.0625. Now, a little bit of the notation here. y1 would really be the y value at 1.25, or used for 1.25. y2 would be y of 1.5, and y3 is the y value for 1.75. So if you remember, we always use the y value from the step before. So there's my 1.5, so this really is the final answer when we get to 1.75. All right, there we go. Another way to write it is with a table. So I have some students who like to write out the equation. Some of us prefer a table, so let's look at example 2. I think I'm a table person. Using Euler's method with 3 equal step sizes to approximate the values of g 3.3, given that y equals g of x is the particular solution of the differential equation x minus 2y passing through the point 3,2. Use a table to organize your work this time. So I know that my starting values for x and y are 3 and 2. My dy dx is going to be x minus 2y. We're going to use the values over here on the left. So this would be 3 minus 2 times 2. So 3 minus 4, this is really a negative 1. My delta x, it doesn't tell me this time. It says I start at 3 and I want to get to 3.3 using 3 equal step sizes. So 3.3 minus 3 over 3 gives us 0.3 over 3, which is 1/10. This is kind of like finding your delta x for the Riemann sum. So our delta x, or h, is 0.1. When we multiply these two things together, I've got 0.1 times the value of that derivative, or the differential equation, negative 1. So this is negative 0.1. So if I take that previous y value that we're using, which was 2, and I add, this is the value in the column prior, add a negative 0.1, then I wind up with 1.9. So we're going to do it again. Remember, my step size was 0.1. So now my new x is 3.1. My y value comes from the line before. It's 1.9. To evaluate the differential equation, it's the x value minus 2 times the y value. My delta x, or the h, is still 0.1. Back here, my differential equation is 3.1 minus 2 times 1.9 is going to be 3.8. So 0.1 times 3.1 minus 3.8, that is a negative 0.7. If we multiply those two things together, 0.1 times negative 0.7 is negative 0.07. So the previous y value is 1.9 plus the previous column, and this leaves me with 1.83. So my new x value is 3.2 because we go up by 0.1. My previous y value is 1.83. I didn't leave enough space in this table, but to evaluate that differential equation, it's 3.2 minus 2 times 1.83. I don't have a calculator right in front of me, but figure out what goes in this box. Your delta x is 0.1. This is 0.1 times whatever you got in that third column. And then this would become 1.83 plus whatever value is in that third column. And when you get that, you should have 1.784. So the next one, 3.3, is using the y value of 1.784. So there's my approximation. I think the table to me makes a little bit more sense. So g of 3.3 is approximately 1.784. There we go. This can be helpful, especially when you have a differential equation that's not separable, like this one. So you can use Euler's method to go through and see what you get. Alright, I made a total mess of that third row, but let's try again. 3.2 for the x, 1.83 for the y from the previous ones. When I use the differential equation, I get a negative 0.46. Delta x remains the same. When I figure out that piece of the product of the delta x in the differential equation, it would be 0.1 times negative 0.46. And then when I put them into that expression to find the final step, I wind up with 1.784. So it's pretty straightforward. I hate the phrase plug and chug, but it really is a plug and chug set of problems. Here's an example that I found online. So this is a picture of the slope field, Euler's method, and the function equation is actually the solution. Alright, good luck with those problems. They really are pretty straightforward. Well, let me know if you have questions.